Okay, so Pure 2 Chapter 3, again, another wonderful resource made by Dr. Frost. So, what we're going to look at today is we're going to look at the graph y equals 2 to the power of x. Because, as you know, in GCSE, we've done a lot of x to the power of, whether it be negative, fractional, or a whole number. We don't really see what happens when we have 2 to the power of, okay? So here we have y equals 2 to the power of x. What I want you to do now is I want you to go onto Desmos, and I would like you to try y equals 2 to the power of x, y equals 3 to the power of x, y equals 4 to the power of x, and tell me what you notice happens. Okay, always crosses 1 at the y-intercept. Does anybody know that? Does anybody know why? It always crosses 1 at the y-axis. That's what somebody said. Absolutely correct. When it crosses the y-axis, our x coordinate or our x value is 0, and we know that anything to the power of 0 is 1. Okay, so this is what we like to call an exponential function. Okay, because where we've seen with linear graphs, you know, there's a bit of a pattern, isn't there? You know, for the gradient, you go across 1, up 1, and this is how it works. But with exponential growth, essentially, if you think 2 to the power of 2, that's 2 times 2. 2 to the power of 3, that's 2 times 2 times 2. Okay, we're raising to a power each time. Okay, this is called exponential growth. And what we're going to do is we're essentially multiplying by the same amount each time. This is like interest, when you think about banks, depreciation. This is what we're doing here. So, what we're going to look at is we're going to look at a few different graphs. Now, I know we've used Desmos, okay? And what you should find, if you put this into Desmos, on the same axes, we're going to sketch these. Now, we know when we do a sketch, okay, we're going to label our diagram X and Y. That's our favourite part, isn't it? Okay, and what do we know? Okay, we have to know a few things. If I choose a few different colours, so my red line is y equals 3 to the x. It's going to look like this, and it's crossing at 1. So this is my y equals 3 to the power of x. We know it's going to cross at 1. If I now do y equals 2 to the power of x. Now, if I think about this logically, 2 to the power of x, 3 to the power of x. If I start doing negatives, okay, let's just think about 3 to the power of minus 1. It's 1 over 3. 2 to the power of minus 1 is a half. So on the left-hand side of the equation, our y to the power of 2x is going to be above the line of y equals 3 to the x, but below it on the right-hand side where it's positive. It's going to look like this. So it's going to be like above here, but then it's still going to cross at 1, and then it's going to be below. Okay, because we know that 2 squared is 4, but 3 squared is 9. Okay, and then the same again with the line of y equals 1.5x. It's going to be above on this side. Ooh, this is a very terrible drawing. But below on this side, if this makes sense. Please do use Desmos. As you know, my drawing skills are not incredible, but I am getting better. And here we know our coordinate is 0, 1. Okay, and this is because we know on the left-hand side, so when x is less than 0, we know that when x is less than 0, 3 to the power of x is smaller than 2 to the power of x, which is smaller than 1.5 to the power of x. That's why we have 3 to the power of x here under on the graph. But we know when we substitute in x is greater than 0, that 3 to the power of x is going to be greater than the line of 2 to the power of x, which is greater than the line 1.5 to the power of x. You just have to know this, because if you were told to sketch 2 of the same on the same axes, you have to understand exactly what's going on. When in doubt, put numbers in and work it out, okay? So, on the second one, on the same axis, sketch y equals 2x and y equals a half to the power of x. So give this a go for me, please. So y equals 2x. We should be fairly happy with sketching. Our graph is never going to go into the negative. It's going to cross on our y-axis 0, 1. Okay, and essentially there is an asymptote on the x-axis, isn't there? Because we're never going to have a negative, y value. Right, a half x. Let's think about what's going on. Okay, and as I said, when in doubt, put some numbers in and figure it out. If I put a half to the power of 0, I know it's going to cross at 1. Okay? But if I put a half to the power of 1, I'm going to get a half. If I put a half to the power of a half, that's actually going to give me 4. Yeah? So what we're actually going to find is this is a reflection in the line y equals 0. So reflection in the y-axis is going to now, our graph of y equals a half x. Oh wow, wait there everyone. I'm going to turn my iPad upside down. Okay, start down here. Oh, that's actually really terrible. There we go. So here it is. This is y equals a half to the power of x. Now again, you can, if you want to, substitute numbers in. But what would be really clever is if you noticed this, that y a half to the power of x, okay, is exactly the same as y equals 2 to the power of minus x, okay, which we know is the same as 1 over 2 to the power of x, which we can rewrite as a half to the power of x. Now, what you also know with graph transformations, is it inside or outside the bracket? Inside. Who does it affect? X. And we're going to divide all of our x values by minus 1. But we should also know that this is essentially, we could write this as f of minus x. And this, as a transformation, is a reflection. Okay? In the line y equals 0. Yeah, it's a reflection in the y-axis. Okay? So, moving on. Okay, y equals 2x plus 3. Now, we know the graph of y equals 2 to the power of x. Okay? The graph of y equals 2 to the power of x is here it is, and we know it crosses at 0, 1. Okay, we now have to, we've got sketch y equals 2 to the power of x plus 3. Now think about it. My x plus 3, is this inside or outside the bracket? Inside the bracket. Who does it affect? X. This affects x. And what are we going to do to the graph? Shift it. It's called a translation to the left, 3 units. So what we have to think, if we are going to translate it 3 units, we know this is 1, this is 2, this is 3. This point here is now going to be translated, is it not? Yeah? Now, if you think about this, when x equals, the other way you could think about this, so whatever this point normally would be is being translated. Remember, this is the graph y equals 2 to the x. Okay? So, we now know if we translate it free, remember this is the graph y equals 2 to the power of x. This here is 2 to the power of 3, which we know is 8. Okay, we know this coordinate is going to be 3, 8. If we translate it now what we find is our intercept is now 0, 8. And this is y equals 2 to the power of x plus 3. Now, you could have done this another way, not by using graph transformations, by is it inside or outside the bracket. You could have essentially said, I know that 2 to the power of anything looks like this. This is the shape. And if I substitute in x equals 0, I get 2 to the power of 3, so I know it's going to cross there. Again, a few different ways. Okay, here are a few more. Now, I've got a graph here called E. E. Has anyone ever heard of E before? What is an exponential? Does anybody know? Nobody knows yet, okay. I would like you to put E into your calculator and press equals, please. Okay, so we should find if we put E into our calculator, press equals, we get a number like 2.7, roughly. Okay, so E is known as, no, sometimes I don't pronounce this right. I think it's, I don't even know if I can say it. Euler's number. It's like E-U-L-E-R. Does anybody know how to pronounce that? Euler's number? Anyway, okay? And it's a mathematical constant, okay? Now, it is the base of the natural log. Now, this is going to become more sense the more we move through this chapter. For now, what I want you to think of E as is, for example, pi. We put to our calculator the symbol pi. We know that pi is 3.14. E is 2.7, okay? So earlier when we had 2 to the power of x, now we have e to the power of x, okay? And e is just a number. So when we're looking at this type of graph, here we have y equals e to the power of 3x. Now we know x, y, that any number to the power of x, the sketch is like this, isn't it? So this is like y equals e to the power of x, and we know that this is 0, 1. We should all be happy with this fact now. Okay, now if I was to draw, y equals e to the 3x. Okay, is it inside or outside the bracket? Inside. Who does it affect? X. What are we going to do to the x coordinates? Divide them by 3. So all of my x coordinates I'm going to divide by 3. So my sketch is going to look pretty similar, apart from on the left-hand side, it's going to be slightly lower than the line of y equals e to x, and on the right-hand side, we're going to be slightly steeper. So this is the equation of y equals e to the power of 3x. Okay, let's think about this equation here. We've got a few things going on. Number 1 is, let's focus on what's affecting x first. Inside or outside the bracket? Yeah, we're just going to focus on what's near the x. So the minus, is it inside or outside the bracket? Inside. Who does it affect? X. We know this is a reflection in the y-axis. So we know the graph x y, we know the graph of y equals e to the minus x looks like this. Okay, and we're going to cross at 0, 1 again. Okay, but this time we've got a 5 on the outside. Inside or outside the bracket? Outside, who does it affect? Y, we're going to multiply our y coordinates by 5. So what we are going to find is this point here is going to change and our graph is going to look slightly steeper. Okay, so when I'm now sketching my graph, my final graph is going to look like this. Okay, my new coordinate here, 0, 5, where it crosses the y-axis, and you can see it's slightly steeper. And this is y equals 5e to the power of minus x. Now, when you notice some of these graphs don't look too different, the difference is if they ask you to sketch two on the same graph, you have to understand what's going where. But it's really good to get some understanding. Now, the last part. Okay, so y equals 2 plus e a third x. Can somebody please tell me the third, inside or outside the bracket? Inside. Who does it affect? X, and what are we going to do? Multiply all of our x coordinates by 3 or divide by a third, which is the same as multiplying by 3. Okay? But what we are going to find is essentially, depending on the scale of our graph, e to the power of a third x is essentially still going to look like this. We're still going to be crossing at 0, 1. Okay? Now, we have this 2. Is it inside or outside the bracket? Outside. Who does it affect? Y. What are we going to do? Translate up. We're going to move it 2. Now, remember earlier I told you this graph will never be negative, so we do actually have an asymptote on the line y equals 0. So now if I was to transform this by a translation, okay, I'm going to move this up. Instead of it crossing at 0, 5, is now, 0, 1, is now going to cross at 0, 3. And instead of my asymptote being on the line x, on the x-axis, it's now going to be on the line y equals 2. So when I draw this, it's going to look, and then we're going to have an asymptote on the line y equals 2. Our y-intercept is going to be 0, 3, and this is the graph of y equals 2 plus e to the power of a third x. Okay? Now, even though we don't write the asymptotes on the other graphs, we do have to know that this will be continuing forever and never crossing the line y equals 0. Okay? Right, test your understanding. You've got this question to do on your own. Okay, so we can see we've got 2 transformations going on here. Well, 3 actually. Okay. First transformation, if I look on this on the outside, I have a minus 1. Okay, this is outside the bracket. I know this is going to be a translation, and I know essentially I'm going to be moving my graph down. Okay, this is a translation. And I'm going to be shifting my whole graph down 1. Okay? Right. I then have minus 2x. Now, essentially, this 2, 3, 4, it doesn't really affect anything if we're not drawing the graph accurately, because our sketch could essentially have any scale. But this negative, on the other hand, will affect it. So the negative, inside or outside the bracket, inside, we know this is essentially a reflection in the y-axis. So our graph is going to be flipped. So if I was to draw this all in one go, okay, if I split it up into 2, y equals e to the power of minus 2x is going to look like this. Okay, and we are going to cross at the point 0, 1, and we have our asymptote. Why have I put... Okay, yeah, so this is just the graph of y equals e to the power of minus 2x. Now, if I was to draw, now I'm going to minus 1, okay? So this is just y equals e to the power of minus 2x. Now, when I minus 1, I'm shifting the graph down. So this coordinate is going to now pass through here. Our asymptote is essentially on the line where y equals 0. If we now take 1 away, our asymptote is now going to be on this line where y equals negative 1. Okay? And then our graph is in fact going to look like this. Okay? Now you can rub the red graph out after. If you need to, just have it there to understand what's going on. Then you can go along and rub that out so that you just have your final graph. Now you do need to make sure that you write down any coordinates. So this is 0, 0 and asymptotes, and y equals 1, because remember, normally we have our asymptote of y equals 0, but we don't draw that on there because it is an axis. Okay? Okay, so I'm going to introduce you into logarithms, what they're used for and what they are. So as we know, many mathematical operations have an inverse. For example, if I had 4 and I put this into my function machine and my function was to multiply it by 3, I'd get to 12. Great. What function machine would I have to put it back into to get back to 4? It would be x divided by 3. Fantastic. So this is x divided by 3. This is my inverse function. Okay. In pairs, very quickly, go through and quickly tell me what the inverse function of each one is. Okay, here we go then. So the second one, x minus 3. The third one, the square root of 16. Oh, yeah, sorry, our function is x. Okay, the next one down. The fifth root of x. Okay, and the last one? Log to the base 3 of x. Now, some of you said logs, which is great. I was expecting some of you to say the x root of, essentially, x, okay, which wouldn't make any sense. But sometimes we don't know how to, 3 to the power of something is 81. Well, we actually do know that 3 to the power of 4 is 81. Just like if we had questions like 2 to the power of x equals 8, we know the answer is 3. Okay, but we know in the world we live in, life's sometimes not fair. And it will say to you, 2 to the power of something is 9. Well, what is that going to be? Now, as mathematicians, we can take a rough guess. It will be between 3 and 4, because we know 2 to the power of 3 is 8, 2 to the power of 4 is 16. So we could even be even more clever as mathematicians and think, well, it's got to be 3 point something low. Okay? But how do we find the exact number? And what we have is the inverse of an exponential function is actually a logarithm, okay? And these functions, logarithms, exist in order to provide an inverse to exponential functions. It's really exciting. So, what we do is we are going to rewrite logs, okay? So, this is what's known as a base. Our base here is 3. Okay? Here we have the power, and here we have the answer. When we are writing this in log form, our log is to the base. Okay? It's always log to the base 3. Sometimes in your calculator, you'll just have the log button. If you just type log button, and it doesn't have a base. This base is automatically 10. Okay, you can change the base on some of your calculators. And then our answer, so we're saying log to the base 3 of 9 equals 2. This is how we're going to change it, okay? So, what I want you to do is think about these questions, okay? If we think about what we've just seen, we know that we can write, so if I do a to the b equals c, this is the same as saying log to the base a, because this is my base, it's still a, of c equals b, okay? So, the other way you can say it is 5 what gives me 25? 5 to the power of what gives me 25? 2. So we know the answer is 2. 3 to the power of what gives me 81? 4. 2 to the power of what gives me 32? 5. 10 to the power of what gives me 1,000? 3. 4 to the power of what gives me 1? 0. Absolutely. 4 to the power of what gives me 4? 1. 2 to the power of what gives me a half? -1. 3 to the power of what gives me 1 over 27? -3. -2 would give me 1 over 9. 2 to the power of what gives me 1 over 16? -4. A to the power of what gives me a cubed 3? Absolutely. And 4 to the power of what gives me -1? What's the answer to that one? Error? Why is it an error? Yeah, because we're not having a negative. Think about this. I'm saying 4 to the power of x equals -1. We've just literally spent 20 minutes drawing graphs of a number to the power of x. And what did we find out from that? We found out that, we have an asymptote on this number, on this line technically. Okay, it will never go into a negative y value. Our output is never going to be negative. So this is a big fat no, okay? Okay, so lucky for you, there are some calculators. Calculators? No. There are buttons on your calculators that will help you. Okay, so first of all, I want you to see if you can try and find this button here and just use it to find the answers to these two questions, okay? Okay, so log to the base 3 of 7, we should have got 1.77124, ... Log to the base 5 of 0.3 is minus 0.74807, ... Okay, then it says ln. Yep, I've got a ln on my calculator. Ln 10. Okay, that's 2.302585. Okay, and then ln of e is 1. Cool. Okay, we ready for a house point? Why is ln of e 1? Good question. What is ln? Okay, I'm going to give you a clue. Log to the base something of e equals 1. What is the base? What is the base? If you go back to our previous slide earlier, do you remember we had log to the base 4 of 4 equals 1. That's because 4 to the power of 1 equals 4. So if we think about it here, something to the power of 1 equals e. What's that going to be? E, absolutely. 10 to the power of 1 is 10. Okay, this is e. Now, log to the base e, as mathematicians, you know we're lazy. Okay? We're not writing log to the base e. We renamed it learn. Yeah? Okay? Log to the base e is actually called learn. Learn is called the natural log of x, okay? And it literally means log to the base e. Okay, then in our calculator we have log of 100. Now you should find that log of 100 is going to output 2. Why? Because in our calculator when we use log, this is naturally, it's computed in our calculator to be the base 10. And we know that 10 squared equals 100. Okay? So this is our calculator and everything we need to know about it. Okay, and then the log graph. You do need to know what's going on with the log graph, okay? We know the log graph is not defined for any value of x which is less than or equal to 0. So our asymptote is actually the x-axis. And we're going to come back to this a little bit later. But what is quite interesting is that the graph of e to the x and the graph of ln to the x is actually a reflection of each other. Okay? And we'll come back to that later. Right, this is my favourite part of the lesson. Laws of logs. Okay. Do you remember when we used to look at different laws of indices? Yeah? We looked at, what happens with surds. We have laws of logs. Now, I wonder, there are going to be 3 laws that I tell you and 3 special cases I would like you to work out. Okay? So, the 3 main log laws are... actually, I'm not going to do it this way. Okay. We know, don't we, that x squared times x cubed equals x of 2 plus 3. Do we not? Okay. If we were to write this as a log, essentially, okay, our base would be x, wouldn't it? Okay, so we know that these laws only work if our bases are the same. So when we have, if I had log to the base a of x plus log to the base a of y, this is the same as log to the base a of x multiplied by y. Okay? This is one law. Right. Second law. Log to the base a of x minus log to the base a of y equals log to the base a of x divided by y. Log to the base a of x to the power of b is the same as writing b multiplied by log to the base a of x. Okay? Now, sometimes when I introduce these log laws to students, they forget, if I had log to the base a of xy, I can rewrite that as this. For example, log to the base a of 30. 30 is the same as 5 multiplied by 6, right? So I could write this as log to the base a of 5 times 6, which I know I could rewrite as this. Do not forget, if we can manipulate one way, we can manipulate another way. Okay? This is just a bit of a... Oh, it's okay. It's just a bit of a reminder. Okay, there's 3 more special cases. 3 more special cases. Okay, I'm going to give you a clue. Log to the base a of a. 1. Okay, there's 2 more. Log to the base a of 1. 0. And log to 1 over to the base a of 1 over x. What could I rewrite this as? This is the same as log of a x to the negative 1, and then using this law here, I could rewrite this as negative log a log to the base a of x. Okay, so these are some laws that we need to know. There is another law which you do have to know, which we'll come to at the end, and this is called the change of base. Okay, and we'll come to that. I'm not going to teach you it now. So here again, here are the log laws, and I know this says it's not in the syllabus. It is in our syllabus, changing the base, but we're going to look at this at the end of the chapter, so please do not worry about changing the base for now. All we're looking at right now is logs of the same base. Do you remember all the laws?
Yeah.
Perfect. Okay, here are some examples. Now I'm going to go through these really quickly because this is how they should be done. Quick and efficient. Step 1. Do they have the same base? Absolutely. If we're adding them, that's actually the same as the multiplication. So that's log of 3. 6 times 7, 42. Do they have the same base for question 2? Absolutely. They are base 2. We're minusing. So this is the same as log of 15 divided by 3. What is 15 divided by 3? 5. Okay, I could sit there and work the answers out, but I'm not. I'm just putting them as one log. Then, for the next one, do they have the same base? Absolutely. But here, 2 log to the base 5, 3, I'm actually going to change that to log to the base 5 of 3 squared plus log to the base 5 of 2 cubed. I know when I add logs, this is also the same as multiplying. 3 squared is 9. 2 cubed is 8. 9 times 8. Log to the base 5 of 72. Okay? Part D. Log 10, 3 minus 4 log 10 to the power of a half. So, first of all, they are the same base. So log 10, 3 minus log to the base 10 of a half to the power of 4. Okay? This is 1 over 32, isn't it? So this is the same as writing log to the base 10, 3 over 1 over 32, which is the same as log to the base 10. 3 divided by 1 over 32 is in fact 96. Okay? So, that was nice, quick, simple, easy. Now, on the other side, I want to write this in terms of log AX, log AY, log AZ. If I am going too fast, ask me to slow down, but we need to be picking up these rules. So, I know, first of all, if they're all multiplied, that means actually, what are we doing with them? We are adding them. So I've got x squared plus log to the base a of y plus log to the base a of z cubed. Now, I know if we've raised to the power, we can actually change that to 2 log to the base a of x plus log to the base a of y plus 3 log to the base a of z. There we go. So I'm going backwards. Okay? Second one. If we're dividing, what are we actually doing? Minus log to the base a of y cubed. We know y cubed is actually the same as? Absolutely. Minus 3 log to the base a of y. For the second one, x and root y. We know root y is the same as y to the power of a half, isn't it? I'm going to do this without showing my steps. Let's see if you can follow. Log to the base a of x plus a half log to the base a of y minus log to the base A of Z. Okay? Anybody need me to explain any part of that? It's absolutely getting into a habit. And remember that this x multiplied by root y is all divided by z. So we have to really show our brackets here. Okay, so a little bit of explanation. Log a root y is the same as log to the base a of y to the power of a half. We know using the rule we can do a half log to the base a of y. Okay? Perfect. And then part D. Now, watch this. I am going to do this slowly, and this is magical. Here we go. Log to the base a of x minus log to the base a of a to the power of 4. Okay, I'm doing it step by step here. Honestly, this is so magical. This is log to the base a of x minus 4 log to the base a of a. What do we know about log to the base a of a? It equals 1. So this is in fact log to the base a x minus 4 times 1, which is 4. Mind blown, isn't it? And incredible. These are called anti-laws. Do you know why? Because they are wrong. This is not correct and this is not correct. Okay? Log of b plus c is not the same as log to the base a of b plus log to the base a of c. Log to the base a of b plus c is just in fact that. This can be rewritten as though log to the base a of b multiplied by c, okay, which is bc. Same here, log to the base 2 of x all cubed is not 3 log to the base 2x. 3 log to the base of 2 of x is, though, log to the base 2 of x cubed. Okay, if I see anyone using any of these false laws, no. Okay, very quickly then. Questions 1, 2, 3. Just do a few from each. Off you go. So now we understand how the laws of logs work. We can now start to actually solve equations. Okay, this is so exciting. So here we go. Solve the equation. Log to the base 10 of 4 plus 2 log to the base 10 of x equals 2. Now, step 1, let's make one log using the log laws. So I am going to do this bit by bit. We know log to the base 10 of 4 is as fully simplified as it gets, so that's okay. 2 log 10 to the x. This can be simplified to log of 10 to the power of x squared. And this equals 2. Okay, now again, this is still not completely simplified. We can still manipulate this. We know that log to the base 10 of 4 plus log to the base 10 of x squared, actually we can write this as 1 log. This is log to the base 10 of 4x squared equals 2. Now, what did we find out earlier? And I am going to put a little star and write it here. We found out earlier that this means 10 squared equals 4x squared. Okay? Why does it mean that? And if you remember, if we had a to the power of b equals c, this is the same as doing log to the base a of c equals b. Do you remember that from a few slides ago? So, we can convert between log and normal forms. So this means that 4x squared equals 10 squared. This means that 4x squared equals 100. This means that x squared equals 25. And x equals plus or minus 5. But We reject the -5 because we are not allowed to log a negative number. And we saw that from the graph earlier. This is not allowed, okay? So we reject the negative, and x only equals +5. But we just have to make sure that we check what's going on, okay? So x equals 5 is the final answer. Here we go. Given that 2 log to the base 2 of x plus 15 minus log to the base 2 of x equals 6, show that x squared minus 34x plus 225 equals 0. This is what I need to show. So, first of all, I know I can write this, the first part is log to the base 2 of x plus 15 all squared. Okay? And then I've got minus log to the base 2 of x equals 6. Okay then we know, what are we going to do? Well, first of all, I know when I take away, this is actually a division, isn't it? So this is the same as writing log to the base 2 of x plus 15 all squared divided by x, and this equals 6. Okay? Now I know from earlier that log to the base a of log to the base a of c equals b. This means that a to the power of b equals c. Okay? So using that, I can say 2 to the power of 6 equals this. So 2 to the power of 6 equals x plus 15 squared over x. Now I can multiply both sides by x. 2 to the power of 6 is also 64. So I'm going to have 64x equals x plus 15 squared expanded is x squared plus 30x plus 225. So that means if I rearrange this, I'm going to get x squared minus 34x plus 225 equals 0. Therefore, proved. Nice and simple. It then says, hence or otherwise solve this equation. Okay, solve it. Again, if you've got a magic calculator, amazing. Or if you've got a brain, even better, because you can factorise this. Two numbers that multiply to give you 225 is 25 and 9. But they add to give you minus 34, so it's minus 25 and minus 9. This equals 0. Therefore, x equals 25 and x equals 9 are the answers. Okay, here you go. 4, 5, 6 and a challenge. If you're feeling really confident, just head straight to questions 5 and 6 and then do the challenge. If you need a bit more practice, start on question 4.
Can you go back to that for a second?
Okay, so solving equations with exponential terms. So first of all, we know the rule that a to the power of b equals c can be rewritten as log to the base a of c equals b. We know this rule, okay? So 3 to the power of x equals 20 can be rewritten as log to the base 3 of 20 equals x. I can literally type this into my calculator and then I'm going to have 2.727. And this is to 3 decimal places. Okay, we're going to apply the same rule to the second question. So we're going to have log to the base 5 of 61 equals 4x minus 1. Okay, we literally just need to solve for x. Log to the base 5 of 61 is a number. Okay, so we're going to have log to the base 5 of 61 plus 1 equals 4x. Now, it's really important that we use brackets because if you put in your calculator log to the base 5 of 61 plus 1, it may think that you're doing log to the base 65 of 62, essentially. So then, what do I do? How do I now find x? I'm going to divide by 4. So in actual fact, x equals log to the base 5 of 61 plus 1, all divided by 4. So x equals, I can type this into my calculator exactly how this looks, and it's 0.889 to 3 decimal places. So here we have our favourite type of questions. What are they? They are quadratics in disguise. They're hidden, okay? Now, we know, again, 3 to the power of 2x using laws of indices can be written as 3 to the power of x squared. So in our case, when we're thinking of our quadratics, so we can use substitution. If you wanted to, you could say, let y equal 3 to the power of x, okay? We know that this is 3 to the power of x all squared plus 3 to the power of x minus 15 equals 0. This is going to give us y squared plus y minus 15 equals 0. Now, this doesn't look like a very nice question. What do we get? Minus 1 plus root 61. I tell you what, let's change this up a bit. Let's change the question, everyone. We're going rogue. So, here we go. This is 3x plus 1. Okay, what do we know about, do we want 3? No, because we're still going to get 3, aren't we? 2 numbers that multiply to give me 15, but add to give me 3. Okay, 2 numbers that add to give me 3. Okay, we're changing this to plus 4, everyone. Okay, this is a plus 4. There we go. So, here's our new thing. And we know 3 to the power of x plus 1 is, in fact, 3 to the power of x multiplied by 3 to the power of 1 using our laws of indices. Okay? So, I could rewrite this equation as 3 to the power of x squared plus 3 bracket 3 to the power of x plus 4 equals 0. Now, I can either use substitution and put y's in here instead, so you can see it easier, or you can go straight to, you know this is a quadratic. We have an unknown number squared plus 3 lots of that unknown number plus a constant, okay? You know this is a quadratic, and we know how to factorise quadratics. 2 numbers that multiply to give me 4, but add to give me 3. I've done it wrong again, haven't I? Okay, you ready, everyone? Wait there. This is a minus. This is minus 3. Okay? No. No. Wait there. This is minus 4. Oh, what a morning. Okay, this is minus 4. Right then. 2 numbers that multiply to give me minus 4. Minus 4 and 1. But I'm going to do 4 and minus 1 to get me 3. So this is essentially 3x equals 3x plus 4, 3x minus 1 equals 0. There we go. I have factorised this. Okay, finally. Right then, so we know that 3 to the power of x equals -4 and 3 to the power of x equals 1. Now actually we're quite lucky because we know anything to the power of what gives me 1? 0. So we know that x equals 0 is a solution, okay, without having to use logs, okay? But what happens here? Yeah, because I'm going to have, remember, it's going to give me log to the base 3 of -4 equals x. And what can we not do? We can't log a negative number, so we reject this, and there's only one solution. And the only solution is x equals 0, okay? Right, let's try the next one and hope this one works better. Are we ready? Okay, so 2 to the power of x minus 1 over 2 to the power of x equals 1. Again, what do we have here, everybody? Hidden quadratic in disguise. Okay, I'm now going to multiply everything through by 2 to the power of x. So, I'm going to have 2 to the power of x squared minus 1 equals 2 to the power of x. Rearrange everything. 2 to the power of x squared minus 2 to the power of x minus 1 equals 0. Factorise. Two numbers that multiply to give me -1, but add to give me -1. No. Again, this doesn't work.
This should multiply by x. So it becomes. Yeah, because I thought it goes through. Oh, no, it doesn't matter. It's the same thing.
Okay, do you know what? We're going to put a pin in this because I don't want it to be a horrible number. Okay, so sometimes what we noticed with those hidden quadratics, we were able to manipulate it all because they all had the same base. Okay, here, if we notice, we've got a base of 3 and a base of 2. So we can't apply the same strategy of trying to manipulate both sides and see if we can make a quadratic or even solve the equation because we don't have the same base. So in this case, when we don't have the same base, what we have to do is put the different bases on each side of the equal sign. Okay, and we're going to take logs to both sides. Okay, now what we're going to do is we're going to take a log to the base 10. So how this works is, so bases are different. Okay, so how this works is we're going to take log to the base 10 of both sides. We're going to have log 3 to the x equals log of 2 to the x plus 1. So you can clearly see here, I don't write the base because if I don't write the base, it automatically means base 10. Okay, and in your calculator, you'll be able to do this. Now I'm going to go back to the log laws. We know to the power of means x log 3 equals x plus 1 log 2. Okay? Now, imagine these logs, they're just numbers. Remember, log 3 is just a number. Put this into your calculator, you're going to get a horrible decimal. Imagine this is like a third. We're just writing it as log 3 for now. Okay, we're going to keep it exact. So here, I have x log 3 equals, I'm going to multiply this bracket. X multiplied by log 2 is x log 2. 1 multiplied by log 2 is plus log 2. Okay? Now, I want to find out what x equals. So what I'm going to do is rearrange the equation. I'm going to move everything with an x on the left-hand side, everything else on the right-hand side. I may have to factor out and then divide, you know? So I'm going to have x log 3 minus x log 2 equals log 2. If I factorise out an x, I'm going to get x brackets log 3 minus log 2 equals log 2. Okay, this means that x equals log 2 over log 3 minus log 2. Now, I can put this into a calculator. When I put this into the calculator, I get 1.7095, which equals 1.7 to 1 decimal place. Okay? Now, it hasn't actually told us here how many we're going to do it to, but it's always good to write down a few, and then whatever you write down, please make sure what you've rounded it to. Okay? Okay, so for question 1, nice and easy, we're just going to take a log. So we're going to have log to the base 3 of 5 equals 2x minus 1. Log to the base 3 of 5 plus 1 divided by 2 is going to give me x. And again, that's just simple algebraic manipulation. When I put this into my calculator, 3 decimal places, I'm going to get 1.232. Question 2. We can see here we have different bases. So we're going to take a log to the base 10 to both sides. So we're going to have log to the base 10, but we don't write 10. 3 to the x plus 1 equals log to the base 10 of 4 to the x minus 1. Now I know log laws, okay? And the laws tell me that log of a to the power of b can be written as b log a. So I can write this as x plus 1 log 3 equals x minus 1 of log 4. I can now expand both sides. So I'm going to have x log 3 plus log 3 equals x log 4 minus log 4. Now what I'm going to do is I'm going to move everything with an x on the left-hand side, everything else on the right-hand side, so that I can get x on its own. I'm going to get x log 3 minus x log 4 equals minus log 4 minus log 3. If I factorise out an x, I'm going to get x is log 3 minus log 4, which equals minus log 4 minus log 3. I can now divide both sides. So x equals minus log 4 minus log 3 all over log 3 minus log 4. Put that into my calculator, it wants 3 decimal places, so x equals 8.638. Now, you might have done this a different way, and you might have log 4 plus log 3, and then on the denominator you might have log 4 minus log 3. That's still the same, because all they've done is multiplied everything by minus 1, okay? So, solve 2 to the power of x multiplied by 3 to the power of x plus 1 equals 5, giving you an answer in exact form. Now, it is clear to see here that we have different bases, so I'm going to take log to both sides, as we know. So I've got log to the base 10, 2x multiplied by 3x plus 1 equals log to the base 10 of 5. Okay, so log laws, what do we know? Log of AB is the same as log of A plus log of B. So I can split this up into log of 2 to the power of x plus log of 3 to the power of x plus 1 equals log 5. Okay, I can now use the log law. Log of A to the power of B is the same as B log A. So I'm going to have x log 2 plus x plus 1 log 3 equals log 5. I'm going to expand and simplify. X log 2 plus x log 3 plus log 3 equals log 5. Okay, I'm now going to factorise out an x. X is log 2 plus log 3. And this equals log of 5 minus log 3. Now I'm going to divide both sides. So log of 5 minus log 3 over log 2 plus log 3. Now we could simplify this further. If 5 divided by 3 was a nice number, I would write this as log of a over b. But it's not. So I'm going to keep it as log 5 minus log 3. But we know that log of a plus log of b is the same as log of a times b. So the 2 and 3 I can multiply together, which gives me log 6. This is fully simplified, okay? Now again, if let's say this was a 6 and this was a 3, I would do 6 divided by 3, which is log 2 over log 6, okay? So you can manipulate this in many ways. If it's a nicer number, do that. So, well done. This is the last section on logs that we're going to be looking at today. Okay, here is the rule. I wonder okay, so we have two rules here. We have log to the base a of x. We could rewrite this as log to the base b of x over log to the base b of a. And log to the base a of b, we can rewrite as 1 over log to the base b of a. For the first one, I know we have a special calculator, and what I forgot to mention was the question said, calculate this as a base 10. So what we'd actually have to do is this. We know log to the base 8 of 11 equals, if we want this in log to the base 10 over log to the base 10, we know the base 8 now becomes the denominator here. And then 11 is essentially our numerator, okay? So, therefore, when I put this into my calculator, my answer is 1.15. The other way we could have shown this, okay, this is one way. Another way we could have shown this is simply this. Log to the base 8 of 11 equals x. We could have written this as 8 to the power of x equals 11. We now take log to both sides. So log 8x equals log 11. X log 8 equals log 11. That means that x equals log 11 over log 8. And what we've done here is we've proved this rule by using what we know about taking logs to both sides. Okay, and this will yield the same answer. It will say change the base in the question if it wants you to do this, okay? For this part here, I can only solve this if the bases are the same, okay? Now, in these types of questions, I strongly recommend having our base as a numerical solution, as an actual number, sorry. Don't change your base to an unknown. Change your base to an actual number we have. So we've got base 5 or base x. Which one are we going to use? 5. Okay, so step 1. Log to the base, I've put LG, wait there. Log to the base 5 of x. That is in base 5, is it not? Yes, we're going to leave it. Plus 6 lots of log x. Log to the base x of 5. Is this in base 5? No, we've got to change this. So we're going to have a little side note. Really, I should have done this up top, but don't panic. log to the base x of 5 equals. Now, using this rule here, if I want to change the base, it's 1 over, and we can switch it, yeah? So this becomes 1 over log to the base 5 of x. So we're going to get 6 lots of log to the base 5, 1 over log to the base 5 of x equals 5. Now, what have we got, everyone? You know it. A hidden quadratic, yes. Again, our favourite. So, you can, if you want, you know that log to the base 5 of x is just a number. We haven't figured it out yet. Okay, you can do one of two things. You can, if you want to do substitution. You can say, let y equal log to the base 5 of x. And then you're going to have y plus 6 lots of 1 over y equals 5. This is the same as y plus 6 over y equals 5. Now we know, what do I have to multiply everything by? Y. Y squared minus 5y plus 6 equals 0. Is everyone happy how I just jumped to that step? I multiplied everything by y, then moved the 5 to the left-hand side. Okay, we should be really confident with that. Okay, now what am I going to do? I'm going to factorise because I can. Two numbers multiply to give you 6, but add to give you negative 5. Y minus 3, y minus 2 equals 0. So that means y equals 3 and y equals 2. So now, this means that log to the base 5 of x equals 3. Can anyone tell me what x is? X is 5 cubed. So x equals 125. For the other one, when we have y equals 2, log to the base 5 of x equals 2. That means 5 squared equals x, so x equals 25. Okay, so I now have our two solutions. Okay, and I'm going to make it explicitly clear. Therefore, x equals 125 or x equals 25. Okay, and just to go back, just so that we're all very confident, from here, y plus 6 over y equals 5. I multiplied every term by y. Y squared, 6 over y times y is 6. 5 times y, 5y. I then moved everything to the left-hand side. Y squared minus 5y plus 6 equals 0. Okay? And then I carried on from there.